Okay. Okay. Hello, everyone. Welcome to today's Polariton webinar. I'm Tenten Chen, who is currently a postdoc student in Professor Wei Xiong's group at UCSD. So it is our great honor to have Professor Jeremy Baumberg from University of Cambridge as our today's speaker. But before we start, I would like to make a few announcements and introduce the future schedule of our Polariton webinar. So first, the Journal of Chemical Physics, they have this special issue of Polariton chemistry, molecules in cavities, and plasmonic media. And the editors are Professor Jason, Professor Shagai, Professor Wei, and Professor Hoel. And you are all welcome to contribute. The submission deadline will be October 16th this year. Let's go back to our webinar schedule. Our webinar will be held every Wednesday at 9 a.m. Pacific Standard Time. And for each talk, the registration can be made through this link or the link we provided in the reminder email every week. And here is the future schedule of our talks. And one thing I would like to highlight is that we will also extend our webinar invitations to postdocs as our panelists. And the first groups of postdocs invited are Dr. Christine Anadotia from University of St. Andrews and Dr. Bing Gu from University of California at Irvine. Future postdoc panelists will be announced soon. Another thing I'd like to mention is that we recently created this Polariton Chemistry online community webpage on Facebook, which allows everyone to share papers and post advertisements and also announcements. You can search by its name. Meanwhile, we have uploaded our recorded videos on this Polariton Chemistry webinar YouTube channel. For those who missed the talk, you can subscribe and watch these videos later. Finally, I would like to introduce the mechanisms of the webinar. During the talk, attendees are all muted. For those who have questions, you can click the raise hand button here, and I will interrupt the speaker at the appropriate time and enable your audio to ask questions. Also, you can type your comments or ideas using the chat function here so that you can share with everyone. For Q&A, your questions, you can type your questions here, and then these questions will be addressed at the end of the talk. For the questions that are not answered due to the webinar time limit, we will collect and send to the speaker after the talk. Now let's move back to today's webinar. It is our great honor to have Professor Jeremy Baumberg from University of Cambridge as today's speaker. Professor Baumberg got his Bachelor of Arts degree in Natural Sciences at Jesus College, University of Cambridge in 1988. He then moved to the University of Oxford, where he was awarded a PhD degree in 1993. During his postgraduate study, he was a student of Jesus College, Oxford, and supervised by John Francis Ryan. Professor Jeremy Baumberg is a leader in nanoscience and nanotechnology, working for much of his career at the interface between academia and the industry. He has led interdisciplinary nanocenters at University of Cambridge and University of Southampton. He also developed novel devices within companies such as Hitachi, IBM, his spin-offs Photonics, and Baseball. He has received many well-recognized awards, such as Royal Society Mullard Prize in 2005, Royal Society Fellowship in 2011, and the Institute of Physics Young Medal in 2013. His current research focuses on constructing nanomaterials with unusual interactions with light, especially ones that could be fabricated on a large scale, which can lead to practical use. His group has developed a range of unusual nanophotonics, including kilometer-scale polymer opals, and they are also exploring what happens when we confine light to 1 nanometer volumes or below. For probing single molecules and reactions, he has also explored how coherent and quantum properties can be manipulated by nanostructuring semiconductors, producing unusual condensates, which can work at room temperature. Today, he will give us a talk entitled as Strong Coupling and Molecular Polaritons in Extreme Plasmonics. Now let's welcome Professor Jeremy Baumberg. Professor, now you can share your screen.
Thank you. So let me just start this off. All right. Fantastic. Right. Yes, it's great. Thank you very much for inviting me to give this talk. Hopefully, my aim is really just to stimulate some interesting thoughts and hopefully some good discussions as I go through this. And I'm going to show you a range of different things that we've done over the years and try and really collect it to this idea of strong coupling and polaritonics. So indeed, there are many different areas here which sort of link together, and I'll try and make that clear as we go along. And I think what I should do is start by thanking my whole group. I mean, there's a huge number of people who are involved, and I'll pick out really the senior research fellows in the group, Bart Denais, Rohit Chekiradi, and Juliana Di Martino for the moment. But there are lots of other people involved I'll try and mention as I go on. And as you'll see, that this work is really strongly collaborative. So particularly, I've worked for many years with the chemistry group of Orange Sherman in the University of Cambridge, but we actually work with many theorists. So Javi Puria in San Sebastian has been with us from the start in a lot of this, and he's worked with Angela Dingesrode, who's now got an independent position in the University of Birmingham, and also Dina Roster has done a lot of the DFT I'll talk about in this talk, which is, and she's at King's College in London, just moving to Imperial. So I'm going to start in this area here. So this is actually, since the, I guess, even when I was working at Hitachi, I started to work on this particular system. So I came from a background of trying to make very fast semiconductor switching devices, optoelectronic devices, when I was at Hitachi. And this was a sort of promising system at the time we were looking at, which is these semiconductor microcavities. So here we have a top mirror structure here, which is many, many layers, which acts as a very, very efficient reflector. So the light is reflected there. And the same thing on the bottom here. So these structures have something like over 100 layers grown, and it takes sort of 24 hours to grow them, but they're atomically perfect. So this is a very, very nice cavity. It's on the order of only a few hundred nanometers wide as a cavity. So it traps light in there. And then in the middle is the cavity layer. And what we can do is we can put particular thin layers which absorb light very strongly and emit light. So this is the first sort of very nice excitonic polariton system. So we have excitons that are sitting inside these quantum wells inside the cavity, and we have photons going around the cavity. So if I draw the dispersion relation, which essentially means if I come in with light from some particular angle, then it has some in-plane component here, K parallel. So if I draw the dispersion relation, I get this parabolic shape here. So that's just because the condition for constructive interference for the cavity mode here means that I have to have a particular K perpendicular. So if I come in at higher angles, I need to have a higher frequency. So I need to have a bluer photon to come in. So this is basically the cavity photon mode, which is trapped inside that cavity. And then what we would do is we would actually grow a very thin quantum well, which had an electronic excitation, so an electron hole pair, which oscillate around each other. So there's like this sort of hydrogenic atom, but for semiconductors, and we could tune this to different energies here. And the trick was to build the system, so when you grew it, you got this system which was strong coupling. So essentially the electron hole pair, the exciton would recombine, emit a photon. That photon would rattle around the optical cavity here before being reabsorbed in the exciton, and then be re-emitted and reabsorbed many, many times before it escaped through this mirror here. So what you got was this strong coupling, this splitting between the two branches here where they crossed. And so you got these new dispersion relations here. And the key thing about this work here is that this dispersion relation is a very strange shape. It looks nothing like a normal sort of particle with mass. It has these strange points of inflection. And I'll show you in a second what happens with that. So the first thing, although this is a particle which is an exciton, it's actually, if you look at the shape of the dispersion here, it's extremely light. So these particles are something like 10 to 100,000 times smaller than the mass of the electron. So they move fast, which is their sort of photon aspect. But they also have this electron hole pair nature, so they're charged, so they have strong Coulombic interactions with each other. So this combination is really, really interesting in this particular system. They also have they're spin polarized, and they're also bosons because they're made of two bosons. So the exciton is a boson and the photon is a boson. So this composite polariton, that's also a boson. So they all want to go into the same state. So they like to go into the same state. They're stimulated into that state by this factor n, unlike fermions. And that means they can condense. So if you excite the system at high energy here, what happens is all the system relaxes down here into this bottom state here, where they live for a time before they escape through the mirrors. And when they're in that state, they can actually phase lock together to form a condensate. And that's what we were really interested in for many years. So really this whole area started in the early 90s when people were trying to make more efficient lasers, these micro lasers, and they made these structures, but they started to see these splittings, which is actually the strong coupling, but they didn't know what they were. They just thought, well, it's the cavity's actually gone wrong. Instead of getting a single sharp line, they got these two lines, and it took some time before they figured out that actually it was this strong coupling situation. What I actually managed to do the first was realize that the nonlinear properties of this system are astounding. So if you inject polaritons onto this dispersion at a particular point on the dispersion here, it allows these nonlinear interactions to take place. And in fact, they're enormously enhanced by the stimulated scattering, by the bosonic nature. So that was the first inkling that you should be able to do all sorts of interesting bosonic things with this system. And then that lasted, and people started to see indeed condensates in the mid-2000s. We started to show there were interesting vortices. We actually showed that you could do these at room temperature and make these condensates. And then there's been a huge plethora of interesting interactions, and Jacqueline Bloch will talk about a lot of these next time. The last things that we did, we started to make these condensates, which I'm showing here, and hopefully you can see these videos. So each of these spots here is actually a condensate. And what we found was we could make condensates that were magnetic. So these are either spin up or spin down. What we're doing is resolving these optically. So we can see in circularly polarized light, in sigma plus light, you see spin up condensates, and sigma minus, you can see spin down condensates. And then we can start to look at these interactions of the condensates. And what you can see in this case here is that they actually, the two condensates want to be opposite spin. Or we can set up the system so they want to be the same spin. So that then allows you to start making lattices of interacting condensates, which is really interesting for quantum information processing and things like that. But actually, in the end, I became somewhat dissatisfied with this scheme, and people are still working on this area. And as I said, Jacqueline will talk about it more. But the problem is it's not very quantum. So although these are condensates, they look rather like classical objects. They're strange, nonlinear interacting lasers in some pictures, which is also like a highly driven two-level system. So it's not really clear. You have to actually get to very large interaction strengths before you can really see quantum aspects. And that's what drove me to this system here, which I'm going to talk about really for the rest of today. So the thing about these systems here is that they generally work best at low temperatures, because essentially it's limited by how tightly the light is trapped and also the strength of the interactions from the electronic system. So that's why it became interesting to see, well, how tightly can you really confine light? And so typically what people have done for confining light is to use modes like these whispering gallery resonators, where the light bounces around by total internal reflection. And so you have modes which bounce around like this. Or this is a photonic crystal. So in fact, there's a mode in here. You can just see that these holes here in this film have been moved slightly. And there's an optical mode which sits in that slab of semiconducting material. Or you can make cavities like this, which are a bit similar to the ones I showed you, only now you make a small pillar out of it so that the confinement is more tight in the lateral direction here. And that can still improve things, but still really, the optical volume is always essentially the wavelength of light cubed. So we're talking millions of nanometers cubed. So when I'm really trying to confine light, I mean, I'm a nanoscientist, that's not really confining light very tightly. And more technically, the issue is because the interactions with electrons or with vibrations or other parts of a system, a molecule system, say, they go as some power of 1 over the volume. So for instance, the light matter coupling with electrons goes as something like 1 over the square root of the volume. Or with the vibrations, it goes as something like 1 over the volume. So this volume here means that these interactions are rather small, so they're hard to look at. So if I want to look at one at a time, that becomes difficult. So this is why I'm going to really talk today about plasmons. And as I'll show you, plasmons allow you to go deep below this wavelength cubed scale. So I'll show you something where you can confine plasmons into these very tight gaps here, where the gaps are on the order of nanometers or even less. And I'll show you how then you can get strong coupling in this sort of system and in molecules or in these 2D semiconductors. And then what I'll really try and show you is where we're going at the moment, which is trying to understand where I can go even tighter confinement, and I can confine light down to the atomic scale, and what we're starting to understand about that. So that's a really interesting system. So we can go back to here, and we saw that the sort of fundamental for a dielectric system is we can confine light to on the order of the wavelength cubed inside the material. If I go to a metallic system, it turns out that changes. And a few years ago, we showed by actually taking 2 nanoparticles here. So these are 2 gold nanoparticles on the end of conducting tips. And we could look optically and electrically at the same time at these. And what we could prove in the end was that as you bring these close together, in the end, you get quantum mechanical tunneling. So an electron on one nanoparticle can jump through the space in between them even before they touch. And because it does that, it shorts out the gap between them. So what that means is there's a quantum mechanical aspect to how tightly you confine light, which is given by when this quantum mechanical tunneling starts. So this DQR, this quantum mechanical tunneling. So DQR is on this order of about 0.4 nanometers. It's not very easy to change. And you also have the diameter or the radius of the nanostructures that you're looking at there. So that's what we thought was the very smallest size that we could ever confine light, on the order of tens of nanometers cubed. And so that still allows you to do something like zeptoliter chemistry. So it's not big. And I'll start with that, but then I'll show you that in fact this was wrong. I mean, or rather, it's not completely correct. And it's not completely correct actually because we can change this R. We can actually take this R down to the radius of even a single atom, and it still works, this formula. And we can show that we can confine light even more tightly. So we'll get to that a bit later in the talk. So what we were interested then is, can we confine light between metals? And as I'll show you, the best thing that we could do is actually make a very, very small gap between two metals. So what we wanted to do is to control this gap size to the nanometer scale. So we started by trying to control that gap size by putting graphene in between two gold nanoparticles. And the problem is that once you've got one gold nanoparticle on here, the second one doesn't want to go into its vicinity. It's very hard to make this happen. So that's not a good system to make it work. But if I instead put the graphene on bulk gold and I bring a gold nanoparticle on top, then it works spectacularly well. And it actually depends on some undergraduate physics that you often learn. So you learn that if you put a charge above a bulk metal surface, then the electrostatic field here can be modeled with an equal and opposite negative charge, the same distance inside the material, and then you can get rid of your metal. So when this gap is very small, it turns out that any dipole that exists inside the nanoparticle will also create an image dipole below it. So it turns out we can actually look at this system electrostatically. We don't really have to understand that the light is fluctuating at enormously high frequencies, but we can just treat the system like that. So this looks like a nanoparticle with an image nanoparticle sitting below it. And indeed, all of the optical modes look exactly like that. They look exactly like a dimer, but they're coupled a bit more because there's a bit more surface here. So this,
Professor?
Yeah, indeed.
Yeah, so we have one question. Sorry to interrupt.
That's good.
Hi, thank you. I just have a naive question regarding a few slides ago. You mentioned that the light matter coupling was scaled differently with volume for electrons and vibrations. Can you explain that?
Yes, I think it'll be easier to do it later in the talk, but essentially it comes from the fact, it comes from the fact that really the electrons are emitting. So we saw the sort of electron emits into the optical field and absorbs back, whereas it's sort of a second order process for the photons. You can almost see it from the Raman cross section. That's probably the easiest way to get it intuitively. I'll come back to that. It's a good question.
Okay, thank you.
Yeah. Right, okay, so I'm just
gonna... Hi, Professor. Sorry to interrupt. We have another question.
Okay, go for it.
So I have a question. So right now, seems like all the graphene and the TMD are both on the metal substrate and support. My question is, will there be a strong screening effect coming from the metal substrate?
That's a very good question. We'll get to a bit later, but essentially the answer is what's important in the gap here turns out to be the polarizability in this vertical direction here. So what happens is when I put my, say, graphene against the gold, you might ask, well, doesn't the gold completely change the properties of the graphene? The answer seems to be no, and it's because essentially there's S-like type of electrons in the gold and P-like electrons in the graphene. That's the best way I can try and explain it. Within this volume, I mean, clearly you can make contact to graphene with gold, but everybody knows in that field it's a little bit puzzling how to make that work well. So it turns out, say, when we look at the properties of graphene in this gap, it looks just like graphene and we don't seem to see doping. So you'd see that in the shift of the Raman frequencies, and you don't really see that. So to first order, it doesn't seem to have an effect, but it's an excellent question.
Okay, that's pretty surprising to me, but thank you.
It is indeed. So we'll talk a little bit more about it as we go on.
Sure, thank you.
You have another question?
Yeah, I think
hello. Hello.
Hello, go for it.
Yeah, so my question is that what sets a fundamental lower limit to the point up to which the light can be confined? Like, is there a fundamental lower limit?
Yes, there is a fundamental limit. I'll show you that as we get through the talk. So it's, yeah, there is a fundamental limit, and we're basically now at that limit as far as we understand. So we'll come back to that question. Okay, so what I'm going to do is try and explain why it's so good to confine light in this sort of region between two metals. So we know already that there's a plasma frequency in a bulk metal, and this is what you learn as undergraduates, which just depends on the square root of the electron density and the effective mass. We also know that we can trap light into a two-dimensional plasmon on a bulk metal surface like this. And that plasmon, I mean, it's smaller than the, you know, this penetration depth into the dielectric above the metal is smaller than the wavelength of light, but not that small. And it's only when we make this metal insulator metal structure here that we can really confine light incredibly tightly. We can also use a very thin insulator metal insulator structure as well. So what we find, if we solve the equations for light and the structure, we find that as we make this gap smaller, surprisingly, the light doesn't get forced out of the gap. There's a mode which really likes to sit in the gap there. And the only difference is it starts to go very slowly. So it travels in this direction very slowly. And that's why this in-plane wave vector now becomes much, much larger than the free space wave vector. Essentially, that means that it's traveling at 100 times slower than the speed of light. So this mode here, which you can just solve very easily, sits inside this metal insulator metal gap. But when we look at such structures, if we look at the spectroscopy of a structure like this, so we put a TMD in the gap here, then we see actually a number of different modes. That's not what we would expect from that. The reason that we get that is because whenever we put a nanoparticle down, we always find this nanoparticle always is faceted. So it doesn't matter how superspherical it might be to start with, as soon as you put it down, the van der Waals interaction is extremely strong and it re-sculpts the bottom of the nanoparticle, and it's always a facet on the order of 10, 20 nanometers. So what happens is you have a discontinuity at the edge of the facet. So this is the insulator metal waveguide, but now what happens is those plasmons, they bounce against the two walls here. So they bounce backwards and forwards, and they form a sort of little cavity. It's a strange cavity because the walls are actually here and here, if you like. There's the sort of discontinuities which act as the mirror, and it's only a few, 10 nanometers or so long. But because the mode is traveling so slowly, that's actually fine. The wavelength, if you like, the effective wavelength is the wavelength in free space over 100. So now I can actually get a round trip where I get a phase of 2 pi. So I actually get modes which can sit in the gap there. And these are the modes that sit there. There's a lowest mode and the next mode and so on. So it turns out, yeah.
Yeah, hi, Professor. So sorry to interrupt. We have another question.
Good.
Hi, sorry to interrupt. Can you explain again why, so you talk about the nanoparticle and a mirror being very easy to make system, but then you said nanoparticle next to nanoparticle, the nanoparticle dimer was hard, but then... That's right, yeah. So the problem about nanoparticle dimers, if we think about they've got facets on them, if you find any way to glue them together, the overlap here is always different. It's very hard to get registration. Imagine you've got cubes. To make perfect, you'd like to make the registration like that. But inevitably what happens is they randomly come together so you get something like that. So this area of contact, that turns out to be the ingredient that feeds into this. You can actually do a very nice model, which is based on the capacitance of this gap. It's an optical capacitance, and it just depends on this area. And as I'll show here, that's why the facet. So this is an experimental issue, but in principle, if one could make perfect... Yeah, no, it'd be completely fine. If one could, yeah, but we've tried that for a long time. If one could beautifully control this, it would be just as good as the nanoparticle on a mirror. What's nice about the nanoparticle on mirror is that you don't care because it's essentially flat. And say you bring your cube down here, it's perfect, right? You just have to make a nice intermediate layer here. There are many more subtleties that we're finding about the shapes of the nanoparticles as well. But essentially, the nice thing is that it's very robust. As long as you can control the facet size at the bottom, which you can even control optically, then you can control precisely everything about this geometry. So what's nice is that you can actually write down an analytical expression for the wavelengths of these different modes here, because it's basically a Fabry-Perot cavity. And then you can derive things like the volume of the cavity. So it just depends on the radius of the nanoparticle and the size of the gap and the refractive index. So we find that the volumes are indeed below about 50 nanometers cubed. So
10 to the minus 5 of the wavelength inside that refractive index material. And you can also calculate what the field enhancement is. This is E over the optical field that you're exciting the nanoparticle with. And so that goes as something like, again, the radius over the diameter. So you can get field enhancements here well over 500. You can also look at what's the lateral size of the field here, and that goes as this expression here. So it's basically dependent on the square root of the diameter times the gap size. So essentially, you have some very simple formula now where you can see that this cavity mode is very tightly confined in this gap here. The problem is that because this K here is so large, its coupling to free space is terrible. So if you just had this structure, if you just have, say, a prism, like something which was just a very small prism that sat on there, then actually would be very poorly coupled to light. What's important is that there's also an antenna mode, which we called L1 here, which is actually a mode which looks like the mode over the whole of the dimer. And what you have to do is you have to arrange for that antenna mode, which again you can write down analytically, to couple to that cavity mode. And when you do that, it's basically like impedance matching. The light will first couple into this mode and then it will couple into this mode, or they're really sort of mixed together. So you can see this paper to see a review. The other interesting thing to see is that this mode here, these antenna modes, because the field of the cavity mode here is vertical, because it has to be across the faces there, so the optical field is always vertical, then this can only radiate out to high angles. So the tightest confined modes in these gaps always radiate to high angles. And if you look at them in optical spectroscopy, you see this ring. And that's a clear sign that you're looking at a Z polarized dipole. So that gives you a good feeling. That's basically the theory I wanted to show. That gives you a good feeling of why the light is very tightly confined. So I'll show you just a little bit of what we did originally. We looked at these graphene samples. You can make graphene of different thicknesses. It doesn't really matter what graphene you use, because the graphene in the gap here is just a very small amount of the total graphene. So even if you use CVD grown graphene, it always looks perfect under the nanoparticle. And you can see already that there are different colors here. And these different colors you can just measure by scattering spectroscopy. So you send light in at some high angle and you look at a different angle. So most of the light, of course, bounces against the flat gold, and you don't look at that. You look at the light in dark fields here, which is which is scattered to a different angle. And that light has gone into this mode that's in the gap here. So these colors tell you basically a lot of the features of the gap, and you can look as a function of the layers of graphene that you have in there. And indeed, you can see the mode redshifts as you go to thinner gaps here, then it will go to longer wavelengths. There's something else interesting going along here, a splitting, which we'll talk about later. So lots of things come out of this. One of the interesting things is normally in plasmonics, if I bring an emitter close to a gold surface, then when I get very close, within about 5 nanometers, I find what I get is quenching. So if I look at the light that's coming out from some sort of emitter in the gap, it gets quenched because it preferentially gets absorbed in the gold. In the nanoparticle mirror situation, that's not what happens, because there's a competition. There's a competition between absorption of light in the gold and radiation out. And because this is a very, very efficient waveguide, what happens is the re-radiation out here, it wins. So the efficiency actually gets better as you go to smaller gaps. So it's completely opposite to the normal nanoparticle. And it's the intuition that most people have for metals. If you bring a chromophore, an emitter close to a metal, then it quenches. And that's definitely not what happens here. We can see emission from chromophores which are within 0.5 nanometer of the gold. And they can be very strong. And I'll show you that.
Hi, Professor. We got another question. Sorry to interrupt.
Good. Questions are always good.
Oh, sorry to interrupt. So can I ask you something very naive? So suppose instead of nanoparticles, I decided to use, say, 2 dyes, like a chromophore dye as a cavity instead of 2 nanoparticles defining.
So what you're trying to do is, do you want to replace the gold by 2 dyes, or just
I just want to understand how much larger would the electric fields be due to the many electrons in oscillating in the
larger. You can calculate it. Yeah, it's the polarizability of the gold is enormous.
So like thousands of times more or something like that?
Yeah, exactly. So essentially, you're getting a factor of 1,000 here, or even more inside that.
Okay, thank you.
Yeah. So I'll show you some data that shows that. So one of the things that we tried to do is to go to a regime which is this strong coupling regime for a single molecule, right? So as I said, that this light matter coupling, which is what controls this, it scales as 1 over the square root of the volume. And to get the light matter coupling, so what I need to do is I need to have my emission line or my absorption line, I need to have it splits by this amount in strong coupling essentially, but I need to have the line width, which is set by the losses in the system, I need to have that small enough. So this is the problem of strong coupling, and we want to make this work at room temperature because we're interested in looking at the effects with chemistry. So essentially what we have is this two-level system here, and what I've said is that if the light matter coupling is strong enough, then what happens is these levels split into two. So I get these two polaritons in the system, and I have to make sure that this coupling is stronger than either the losses, the phase scattering of the two-level system, or the losses from the optical cavity. So you can plot the conditions for that on a graph of the volume here against the quality factor. So you get a nice graph like this. And the strong coupling condition is this green line that I've shown there. And you also can look at the Purcell effect, which is how much you're enhancing the emission rate, which we'll come back to as well. So this is the dielectric boundary, essentially what I showed you before, that the volume when I'm using dielectric confinement can't get below that level there. And all of the typical ways of confining the light are stuck up here, right? Because the volume of the cavity is not small enough, which means to get strong coupling, you've got to be in this domain here, right? So you're sort of in this domain there. And so you need to have very high Q factors. But the other thing you need is you need to be at very low temperatures. Because the other thing that's important is typically at a temperature T, the interaction with a two-level system, this gamma, is always going to be around KT. In that case, KT corresponds to this sort of quality factor here. So that's why to get single molecule strong coupling, if you're doing it in a dielectric system, you always have to cool the system down, and then you're not really doing interesting chemistry. To do interesting chemistry, you've got to be in this region here. So you've got to be in the strong coupling region and able to access it at room temperature. And that's where the nanoparticle emitter sits, or any very strong plasmonic structure, you can get into this region here. So you need volumes which are less than 10 to the minus 5 of the dielectric volume. The other thing that I said, we have another question.
Yeah, we got another question.
Okay. Hi, Gino.
Hello.
Hi.
Am I audible?
Yes.
Yeah. Professor Baumberg, I have a question from your previous slide. You talk about the enhancement. My question is that is this related to the Purcell effect you're talking about, or just normally we see with normal Fabry-Perot system, or something else that waveguide does?
So you can imagine it like this. The light is being trapped into this gap here, right? So the light is being squeezed. So that's confining the light. If you like, all of the light that's striking the nanoparticle here, all of that gets squeezed into this tiny volume here. So that's why, so essentially that's why all the electrons are involved. It's like this huge antenna on this tiny region.
All right, okay,
yeah.
okay.
That's good. So the other thing that's important to this gap region here is that the optical field, as I said, is in this perpendicular direction. So if I want to couple to an electronic state, I have to make sure its dipole is also vertical. So we have to make sure that the die is vertical. So that makes it a little tricky to happen. So what we did then in this system is that we used a sort of scaffolding system. So because die molecules, anything which has got extended conjugated system tends to want to lie flat. Any ring system tends to want to lie flat on the gold. Just as we were talking about for the 2D systems, right? The graphene and everything like that. Most of the dipoles in those systems are in play. So they're not really good to couple into this system because the fields we need to have them vertical. So what you have to do is you have to make it stand up. So what we did was we used a molecule called a cucubitrol, which allows us to scaffold the dyes vertically. When we do that, we can actually go from the situation when we look at the scattering. This is the scattering, and it's nicely around 650 nanometers of just the empty CB. So we remove the dye molecule, and we can see these very nice scattering spectra. That's our cavity mode. And then when we put the dye in there, which is vertically oriented, we can see that we get this very nice, strong splitting here. And we can see, it depends on how many dyes we have in the gap, that this splitting varies. So what's happening is that we start off with a molecular electronic state, if you like, a homo-lumo state, a dye state there, and we're coupling it to this plasmon, and that coupling is so fast that what happens is we create this anti-crossing here. So these are sometimes called plexiton states. So this is really nice because it's at room temperature. You've made them from solution. It's an ambient condition, so you can do chemistry. It's extremely robust. You make billions of them, and I didn't show you, but they're basically all the same everywhere over the sample. It's very low cost, and it's really stable, with some caveats that we should talk about. So this opens up really a whole nice amount of experiments. So for instance, we should be able to do photon blockade in the system, that in other words, as soon as we put a photon into the system, it should behave differently. And indeed, we start to see that now. We should be able to do sort of quantum chemistry, I'll talk about in a second, and all sorts of nonlinear optics. So quantum optics and quantum light emitters should be possible in this system. So that's what we actually did originally. I'll show you a little bit more of that as well. So this is just, as I was saying, this is a whole load of different samples, and you can see, you know, each one of these is a particular nanocavity or nanoparticle or mirror sample with a dye molecule in, and they all of them have this nice anti-crossing, and you can just plot this out. And because they have slightly different sizes of nanoparticles, the most difficult thing to ensure is that the diameter of the nanoparticles is all the same. So even if you try very hard, you have typically 3 to 5% size variation, and that's what gives you a variation in the tuning condition here between the plasmon and the exciton. So you can actually see this very nice strong coupling going on there. So what we think is we have mode volumes on the order of about 36 nanometers cubed, but the Q is not very high, but that's fine in this system. And that leads to strong couplings of around 400 millielectron volts or so. Now, one of the ideas, and I guess the ideas that many people here are interested in is, well, okay, can you indeed use that to drive chemical reactions in different ways? And the idea, I mean, this is a very nice sort of picture. The idea is you have a picture something like this, is that this is your ground state manifold here. And so what you'll see is that if you then replicate that at, so you assume that putting a photon in will bring you up to a state here, then these two, the excited state manifold and the ground state shifted by the photon will now interact, and that will produce this strong coupling here. And the idea is that you change the shape of this excited state manifold. So for instance, you get a trap here. And what that would mean is that instead of this pursuing down in here to give you a reaction, that it would actually do something different. It might not do a reaction. So far, I mean, it actually looks incredibly interesting and really promising, except so far, mostly what's been seen as a suppression of reactions, and we can talk later about why that's going on. And one of the reasons is that people are using many molecules and lots of modes of light. Nobody's really yet got to the stage where looking at single molecules, single cavity strong coupling. So that's really where we get to. I just would mention that you can also do this with transition metal dichalcogenide systems, so 2D monolayer systems. But the problem about these systems is if you're looking at the exciton, so typically if I look at the electron hole pair in these systems, which people look at, their dipole is in plane. So although it looks like it should be really promising to use this system, it's not. So because what I really need is a dipole vertically. So a single layer, so people have managed to see, so when you're out here, this region over here, so the dipole, if you like, the fringing field, if I draw my nanoparticle on my mirror here, so although the field looks like that here, it sort of bulges out a little bit at the edges here, but it's much, much weaker. So although you can use the field out there, there's a little bit of in-plane field there, it's much, much weaker than the vertical field, and typically you have to use larger gaps. So that's why people have used larger gaps and fringing fields, but it's not a very good system to work in. So you have to use more layers here, and so we're not convinced about this being a way forward. It'll be interesting to talk with people about that. Now, what I didn't show you so far was making this deterministic. So far, what we did was we made the nanoparticle or mirror system here, but the molecule was at a random position inside the gap. This is just sort of fictitious, really. What we really want to do is to control exactly where we put this molecule. And to do that, we were working with one of my colleagues' groups, sort of Kaiser and the Cavendish, and we designed this DNA origami. So this is DNA which is folded up into a very precise three-dimensional shape. What we can do is use that to bind down onto the gold. So there are tags which will bind onto the gold, and then they'll bind the gold nanoparticle into the middle of the DNA origami to make the nanoparticle on mirror geometry. And then we have this molecule which we can put in any position here on the DNA origami. So we started with using CY5, but we can use very many other molecules. And it's a bit like a breadboard. We can actually put the molecule at any position inside that gap. And what we're going to do is we're going to use it to actually record the field distribution inside the gap. So for what we'll see typically when we look at these, we have one dye molecule in there. And now what we're doing is we're looking at the photoluminescence, the emission. And as I said, even though this gap is very small, we can see the emission very nicely from this single molecule. And we can see it for a certain amount of time. And then at some time, we break the molecule. It bleaches. We can also see the scattering spectrum change. This is not quite, it's sort of nearly in the strong coupling regime. And what happens is when the molecule breaks, it no longer creates strong coupling and we get the collapse back just to the cavity mode here. So that's the cavity mode there.
Hi, Professor.
Yeah.
So we have another question. Sorry to interrupt.
That's good.
Hi, Professor. I have a question regarding the TMD system you described.
Yeah.
So recently, people also developed the Janus structure, which is the transition metal layer is sandwiched between one layer of S atoms and one layer of Se atoms. So for that system, they have a auto-plane dipole.
That's true. There are a couple of different ways to do it. You can also use a type 2 system. So essentially tungsten diselenide versus a manganese disulfide. So there are a number of different ways where you can try and get vertical dipoles. None of them are completely easy to get, but indeed that's exactly the reason you want to do that. You want to create an outer plane dipole so you can couple efficiently in this system.
Yeah, I just wonder whether that would be a good system.
No, there are different ways to do it. It's not totally simple. That's the main thing. So,
okay.
It's easy to do with molecules, as I'll show you.
Okay.
So what we do in this system here now is that for a particular sample, we use a DNA origami where we can trap the molecule in a particular position, which is X away from the center of the gap there. And then we'll look at 1,000 or so nanoparticles on mirror. We've automated everything and just look at the enhancement of the light. So this is basically the enhancement we see of the light for when the dye molecule's in the center, and these are for different distances away. And what you can see is that we're actually measuring a big enhancement here. What we're in fact doing is we're measuring exactly this optical field enhancement laterally. And I showed you before, it was essentially given by the square root of the diameter of the nanoparticle and the thickness of the gap. So on the order of about 10 nanometers. So that's basically what we measure here. So it's surprising it's so good. I mean, it's not obvious that this DNA origami structure can control the position to within a nanometer. But that's what seems to be going on here. We can also see the enhancement of the Purcell factor, but it actually, it's already over 3,000. And in fact, the dyes emit far more photons than they normally would here. They go around an emission event much, much faster. So it's more difficult for them to be quenched in the system. So you can look at this paper if you want to see some more about that. What we can also do is show that these are actually really quantum emitters. So we can do the same trick, and now we're going to excite the system with a pulse, which I'll show you why we do. So these are slightly different dye molecules. Basically, the absorption of the dye has that's the absorption, and this is the emission. And then we have to decide where we're going to tune our cavity. We have to decide if we're going to tune it to the absorption or the luminescence or somewhere along here. You can't get strong coupling in both the emission region and the absorption region simultaneously. You have to choose because they're different wavelengths in a molecule. So that's not so obvious. So if you look at the luminescence of this dye molecule in solution, then you'll find it's a couple of nanoseconds just as you expect. But inside the gap here, it's much faster than we can measure. There is no way, in fact, to measure the correlations of photons because the emission is on the order of the splitting, which I was showing you before, on the order of 50 to 100 femtoseconds. We don't have single photon detectors which work that fast. So that's why we use picosecond pulses here, so we can look at the correlation. So people who understand, who've seen this sort of work before, essentially what this is showing you is that the probability that only a single photon comes out of this construct. And this dip here for 0 time delay shows us that indeed this is a quantum emitter. But it actually depends on where we excite the system. So depending on, if we excite at higher energy, we find it's more likely that we get 2 photons coming out. This peak here shows that in fact 2 photons come out at once. So that's probably something about the cascade, but it's still not really understood in the system. Of course, here we can actually we can use this to put 2 molecules or 3 molecules or 4 molecules at completely specified spacings. So we're doing a whole lot of different things about this. So what I'm going to do, given the time, I think I'm going to go to look at how much we can go further than this. So what I'm going to show you is an experiment which is basically scaling down the gravitational wave detectors that we use by a factor of 10 to the 13. So essentially, what we have is, the people realized already in the 1960s that the interferometer that makes up gravitational wave detectors has a problem. And the problem is that the mirrors at the end of the cavity can vibrate backwards and forwards. And they vibrate backwards and forwards because the light, when it bounces against them, exerts a pressure to push them. And because these mirrors are suspended to keep them isolated from all of the earth around us, then they can actually vibrate backwards and forwards. But as they vibrate, they change the cavity length. Therefore, they change the light in the cavity. So what it shows you is that they couple the intensity of light in the cavity, which is just a term which looks like this, with the position of this mirror here, which is a term that looks like this. So this is called optomechanical coupling. And people have actually measured this. Now they've scaled this down to micron scales and made lots of little microfabricated Fabry-Perot cavities like this. And they work the same way. But even in these microfabricated cavity systems, the problem is that the coupling constant here in front of this, G, is very small. It's nano-electron volts. So in other words, essentially the temperatures that you need to cool the system to see this effect are on the order of millikelvin. So that's why people are taking huge steps, and it's very complicated to do. The interesting thing about the geometry I've been showing you, this nanoparticle on mirror, is that the equivalent G, which is proportional to 1 over the volume here, is therefore scaled up very, very strongly. So now it becomes comparable to room temperature. So we can start to see some of these effects at room temperature. So the way we do that is we actually look at this system here. So this is looking at the vibrations now of the molecules. So this is the vibrational ground state here. And when I excite the system with a photon non-resonantly, I have some virtual state here. I can excite the system and it eventually emits a Stokes photon and ends up in this first vibrational state here. So normally, when I excite the system with a laser, there's some probability that the system will emit a Stokes photon that comes out at lower energy. So this is wavelength in this direction or energy in the opposite direction. So I also have the possibility of going the other way around. I can actually first go up to here and then come down to the ground state. So then I'm going to get a higher energy photon coming out on this side here. And the ratio of this intensity to this intensity here essentially tells me the population of this state here. So if I analyze this ratio, actually I find out the thermal population and I can measure the temperature. And it's now a nice way to measure temperatures. So now I do this experiment in a nanoparticle on mirror. And what I do is I cool this down to 10 Kelvin, which means that there's no occupation of this first excited state vibration. So indeed, I don't see anything here. But if I keep on watching, suddenly I see some amazing effects. I see extremely strong emission here, which is matched by emission here. And if I was to calculate a temperature there, that would be thousands of degrees. So more than the melting temperature of gold. So clearly something else is going on. And this started us on a track of trying to figure out what was going on. The nice thing is that we can actually, because I said this G, this optomechanical coupling here, depends on 1 of the volume, but we actually know all the factors in here. So we can actually do a power dependence very rapidly as soon as we see this. And we can actually, from the number of photons we get out, we can actually extract this G for a particular one of these lines. So in this case here, the G that we found was 41 millielectron volts. So what we can do is we can make a histogram over many, many different samples, and we can see that these Gs vary around 40 millielectron volts or so. And if we feed that into this formula, we find that the optical volume is much less than we expect. It's now less than a nanometer cubed. So this is what the data tells us. The data tells us that if we just take this data at raw value, then indeed what we're doing is we are indeed measuring the occupation of this state. We're vibrationally pumping the system, but extremely efficiently. And that means the optical mode is actually extremely small. And the only way that we can understand that is that it's actually coming from a single gold atom. So if you look in the very center of this nanocavity gap now, so this is the field of the gap, this is already the extremely enhanced optical field here, we get an extra enhancement. Whenever I get a gold atom pulled out of the facet, what happens is it actually has a concentration of optical field exactly like a lightning rod. So this is a lightning rod on the scale of a single atom, which you really have no right to expect. And this is a classical calculation, but if you actually do a time-dependent DFT, which is very difficult, you actually see the same thing, and it matches the classical calculation very well. So enormously surprisingly, you can actually account for this gold atom here using entirely classical theory. And it's probably because the electrons in the gold here can go in and out very quickly. They're still free gold electrons. It would be different if we pulled the gold atom completely away from the facet. So a gold atom in the gap here would be completely different. But as long as it's attached to the facet, essentially it gives this a very strong optical field. The other thing that you can see is that the field gradient here is extremely high. So what it means is now that the optical field is varying along the length of a single bond. So what that does is it breaks all of the selection rules in the system. And indeed, we think they're like forces which are actually pulling out this gold atom here. So the net result is that we actually see single gold atoms being pulled out. So we can try this with a molecule which has got a CN group at the end here. So this CN group is nice because it has a particular vibration around the 2200 wave number region of the spectrum. So we can see that on its own. And what happens is as soon as this gold atom gets pulled out, we see only, because the optical field is very strong in the vicinity, we see this particular bond here. So this line that I'm seeing here is a single CN bond. So now you can see single bonds at room temperature, and clearly it's shifting around all over the place. So that's what we've been able to understand more recently. You can also see that the ring modes also shift around because, of course, they're electronically coupled, and there's lots of features going on in here. We can actually use DFT to match very well what's going on. And indeed, it's exactly what we predicted. There's a coordination bond between this gold atom here and the nitrogen. So we can measure the strength of that. And what's happening here is that the strength of that bond is varying around in time on milliseconds to second timescales. So we're still trying to understand why that is. We can also see that actually more of the picocavities come from the bottom metal than they come from the nanocavity, from the nanoparticle. Most of them come from the facet below. And we can do all sorts of things with this. We, for instance, now speeded up our time resolution to the scale of 10 microseconds. So we can start to see much faster, and we can start to see individual molecules flexing. So this becomes a really nice way to watch individual molecules and indeed sort of push them around. So just to end up, I'm going to show you something. We can come back to that, but I'm going to show you one final thing, which is just that you can actually use these for devices. So what we've done here is we've used in the gap, now we've used an electrochromic system. So we've taken the gold nanoparticle and we've coated it with polyaniline, which is an electrochromic polymer, and it can do this redox change between oxidized and reduced, and it changes its refractive index very strongly when we do that. What that does is it changes the color of the light that's trapped in there. And you can just see this by eye as we go between reduced and oxidized states for a single nanoparticle or mirror. So what we can see is that we can go all the way across the spectrum, essentially. The nice thing about this is that we can grow these in bulk quantities, and then we can assemble them and spray coat them onto a metallic substrate. So we actually scale this up. So these are sort of plasmonic pixels. We call them E nanoparticle on mirror. And what we can do is we can just change the color by changing the voltage. The voltage that you need to change them is on the order of something like 0.4 volts. So there's a very, very low voltage, but the system is bistable or metastable because you're essentially doing redox on this polymer. And as long as you exclude oxygen from the system, it will stay in the same state. But because the distance that you need to pull electrons in and out from the system is so small, you can actually drive the system very fast. We have some evidence that you can actually drive it, even at megahertz frequencies, but certainly greater than 100 hertz. And the other nice thing about this is it's completely scalable. So the thing that we're really interested in doing now is, can we actually make building scale coatings where you can change the color on the building? So for instance, can you make it go from black to reflecting silver just by changing the voltage? And can it even do that itself? So you can change the heat load on the building. That's the sort of thing that we're trying to do now. So what I hope I've given you in this talk is, I hope you're now convinced that using this scheme, we can trap light incredibly tightly to the region of certainly tens of nanometer cubes and below. But also that what we can do is that we can couple these to anything that's in the gap. So as long as the dipoles are vertical, then we can actually get strong coupling in the system. We don't understand a lot about it, but we can see even more that when we pull individual gold atoms out of the facet, we can get this very strong additional electromagnetic field enhancement, and that allows us to do optomechanics in the system, some sort of strange molecular optomechanics. And you can even take this into sort of the application space as well as looking at sensors as well. So what I think I'll do there is I'll stop and open it up to more questions if people want to ask them.
Yes. Hi, Professor. Thanks for your wonderful talk. So we do have several questions, and it's time to answer them.
Fine.
Oh, sorry, this is very nice talk. So I just have some questions I want some clarification of. So the first one is, at some point in the talk, you were mentioning this dilemma of coupling to the absorption band or the emission band. And first of all, I didn't get if you were doing strong coupling or just Purcell effect. And then can you repeat the conclusion of what was the best strategy in that situation?
It's not very clear what the best strategy is. So we now have, there are various theory groups trying to understand. The system was already published last year. There really isn't a full theory for this system, because what you have to do is you have to also include the relaxation in the molecular system. So you need to dress all the vibrations in the system, and not just a single mode, because you have also row vibrational relaxation here as well. So you actually, so it's easier somehow in a semiconductor system where we don't normally think about sort of shifts. We think about essentially in a semiconductor system, it emits at the same energy because the phonon relaxation is slower. That's absolutely not true in the molecular system.
Yeah, but so experimentally, what are you getting? Experimentally, what are you observing depending on whether you couple to the absorption or the emission?
Here, we're in a system here where we were trying not to be in strong coupling. We also can go into strong coupling here, but actually when we're looking at this, we're trying not to go into strong coupling at the moment. We're just on the edge of it. Yeah?
Yes, but then okay, so when you couple, say, to the absorption band versus the emission band, what are the two different behaviors that you see in this
At the moment, what we're mainly doing is we've looked at the emission in the system and previously looked at the absorption band. So indeed, it's correct. So we're actually trying to get to the system where we have, so in fact, what we're trying to do is we want to make smaller gaps in here. So with the DIN origami, it's hard to make the very smallest gaps. So what we have are new designs where we can make this gap much smaller. And in those systems, now we can get strong coupling. And so we can investigate exactly that range of behaviors you're talking about. So it's a very interesting question. We're trying to beat the theorists to that.
Okay, thank you. And very quickly, so you were mentioning that at some point you were seeing these strange effects that where the temperature could be, say, thousands of kelvins, and that was obviously not true. So what was the conclusion there? Can you repeat it?
So yeah, that's this data here. When you look at this data here, the conclusion is that when you I'll just start showing again. So when you look at this system here and you look at that ratio there, I mean, it's almost basically the same intensity. So it's thousands of degrees. The reason it's not thermal, so we normally say it's thermal because we're in an equilibrium system. We say that the population of these states is thermalized. Mm-hmm. But what's happening is here is I'm driving this so fast, the G is so large, that I actually I excite many of these. Mm-hmm. And it's not thermal, I excite them before they can relax. So what I get is the instantaneous population in that state, which is dependent on G.
I see. So this is a non-thermal population. This is a non-thermal population. An effective temperature. Okay, thank you.
Yeah, it's an effective temperature of thousands. But you know, and what's interesting is each of these lines here shows a different temperature. So, and the reason it shows a different temperature is when we look at the molecular coupling here, then that molecular coupling is interacting with this peak cavity mode in different ways. So the individual optomechanical couplings are different. So their effective driving is different.
What is the frequency of the mode that you're probing?
So these modes are, I mean, they're all the way from 400 to 1500 wave numbers. We see this everywhere across the bands. I mean, here you can see the peak cavities at from 2000 all the way down. You can see them in the lower wave bands as well.
Thank you very much.
Cool.
Yeah, we got another 2 questions. So
hi, this is a very nice talk. I just have a quick question. So you didn't talk about a molecular orientation much. I see some of the molecule can sit straight up, but do you always control the orientation, or you also see orientation effect?
That's a really good question. We argue about it a lot in the group, because now we have a way to look incredibly precisely at the molecules. And so the more we look into it, the less satisfied we are about people's, I mean, often the STM community has tried to look at the organization of molecules. Here, of course, I'm using a self-assembled monolayer, not a single molecule. So these tend, if I have rings like this, they tend to stack and sit vertically. But they're still tilted. I've drawn it wrong here. They're much more like this. They're tilted in some direction here. Now, so the tilt is something that varies with the stacking and the type of molecules. Because the field is vertical, of course, we see only a particular part of the Raman, and indeed it seems to be correct that we can sort of, if we get better at understanding this, then we should be able to predict from the Raman spectra, the intensities, exactly what the orientation is. The problem is what people have already alluded to as well is that you have a huge number of electrons very close to the molecule. So what you have to understand is how do all the dipoles in the molecule react to these image charges here? So the phonons can also move from that. And so this is also a bit like chemical shifts. There's a whole confusing literature in the Raman scattering community about all these effects. So the problem is that when you're making gaps that are now a nanometer, or we even made, here we have some molecules, I was going to show you, this is a bisphenolcyanine molecule that we're using, where the gap is 0.4 nanometers. And we have a rare earth in here. We can change many rare earths in the gap here. So there's no way that we can really use classical theory to predict this. And indeed, when we look at the modes that we see, they're not predicted by classical theory or the quantum theory. So it's really not clear what's going on. And that's a bit of a similar question to what happens when I put a TMD in the gap here. So it's really not understood how you bridge the classical and the quantum domains here. So the quantum domains of your emitter or your DFT in the middle here, and classically you need to treat a much larger region of gold atoms. So this is, I think, a huge challenge in the field at the moment, which is really interesting.
I see, thank you.
Yeah, we got another question, so.
Hi, Professor, really nice talk. I just have a question regarding this Raman spectrum. So when we explain that with respect to time, you can see a shift of the Raman frequency, that your Raman frequency for the CN bond, I can see that it shifts to the lower energies. So could it be a fact that, it's just basic from my understanding, it could be a fact that you have a complete shifting of electron density from the triple bond to electron due to this coordination bond formation, because of which the cyano bond acquires a double bond character?
Yeah, that's exactly what happens. So in fact, what you can really do is you can measure directly the electron density in this bond as a function of time, and therefore in this bond as a function of time. So we in fact have something like 0.02 of electron resolution inside these bonds now from this. So that's sort of what's in here, but we're doing more of it at the moment because now we can fit the DFT spectrum through the whole molecule. So what we can do is reconstruct the whole system. But yes, exactly right. Essentially, as the gold atom becomes close, it steals electron density from the CN bond into this coordination bond here. And that's what you're very directly seeing here.
Thank you, Professor.
All right, any questions? Oh, so we got another question from Shaowei Li. So I'm going to, yeah.
One more question. So for this page, you mentioned that you have a single atoms on the top layer. How did you determine that? And why is single atom matter?
It's a really interesting question. So what it turns out is that when we make these structures, it doesn't matter what the nanoparticle or the substrate looks like. The forces on here seem to be sufficiently strong that we always get a 1-1-1 surface, we think, on the top and the bottom. And we can tell that because if we look at Raman spectra, so in this system here, we've collected millions and millions of Raman spectra. And most of the time, we just see these lines here, right? Which is just what you expect from the normal gap. It's only very occasionally we see this extra thing happening. And that matches what happens when a single gold atom gets pulled out by about half of its diameter, right? So what happens, and the model sort of shows it works well, is that we get an extra optical field here. And because the Raman scattering strength goes as the optical field to the power 4, then the extra sort of 3 to 5-fold enhancement here gives you a 100-fold enhancement of the bond, of the Raman scattering from that bond. And that's why the strength here is about the same as all the other 100 molecules that we're seeing in the gap. So this is from 100 molecules, and this is from 1 molecule. And it's coming from this enhanced optical field here. So all we do is we look at the data, and it sort of tells us that this is what has to be going on. So what we can also do is we can do, for instance, power-dependent measurements and temperature-dependent measurements, and it shows the probability of creating this. We can see is thermally, I mean, it's actually, we're driving it, and it gives you the energy for doing this. And that energy is exactly what you expect from what people have measured for the add-atom energy of gold. And we've also done it for silver, and it matches the add-atom energy for silver. So from all these measurements, we're fairly happy that what we see here is just a single gold add-atom. Now, if I raise the power, I can see a second one appear, but the second one may be a different distance here, so that mode appears down here. So I can distinguish whether I have 1 add-atom or 2 add-atoms, and so on. Sometimes I don't know if I maybe pulled 2 atoms out at once or not. And for that, we're really trying to understand what sets the intensities there, which should tell us this. So I think it's fair that we know some of what goes on. We're very convinced it's gold atoms being pulled out of a single crystal facet. We can stop it if we actually stop it in some ways now as well, which makes sense. But we don't know some of the details of exactly how it goes on, but now we can start to look at them.
Well, in this case, since it's a fairly symmetric system, the substrate and the nanoparticle since it's all modeled as a kind of flat surface, have you tried to actually put individual atoms on the substrate and then put the molecules on top of it?
Yeah, it doesn't work. I mean, I think it's a very interesting thing to do. We've been playing with this a little bit, and we're surely going to publish some work where we've done some things a bit like that. The problem, if you're using gold, is that what happens is it seems that from a SAM, the SAM is a very robust, the Young's modulus of the SAM is actually higher than that of the metal. So essentially it pushes the gold atom back into the metal when you make this structure. The other thing that people will often say is it looks symmetrical, but of course you prepare it by making the SAM on the flat gold first, and then you bring the nanoparticle on top. And it turns out that it is indeed asymmetrical, and we can really clearly see that. So we know we've done a few systems where we can see that that asymmetry indeed gives you more of a chance from pulling the gold atom from the bottom from the top, and we're trying to understand what controls this. So, I mean, it's an interesting way of actually trying to visualize what really goes on in the gap here.
Oh, thank you.
Good questions, though. Very good questions. I wish I could answer.
Yeah, we have the one more question, but we only have 3 minutes later. So
Okay.
yeah, so we better cut it short. Yeah. So yeah, maybe Peigang, you can ask.
Hello, Professor. So in your first few slides, I saw that in those traditional cavity, there is a lot of work done in investigate spin of the photon. And
yes.
Question that in this cavity, how can you? I mean, is there any advantages to investigate, for example, some chiral molecules, or investigate some chiral things?
Yeah, it's a very good question. So the main difficulty is that I showed you that the mode is vertically polarized here. So if the mode is vertically polarized, it can't carry any chirality.
So
you have to make a more complicated system to do that. And
so
as far as we can,
sorry. So for example, can we use like a cube or like more such nanoparticles to?
If you don't want to use the vertical mode, then you can do it. But the problem is if you're using the cube, the problem is that you have to use a bigger gap because then you want the in-plane mode and that gets squeezed to very low energies. When I take a cube on the mirror, because it's got a large facet, it's basically like what happens when the facet gets very large here. So what happens is the mode goes off into the infrared and then you can't get it resonant with the molecule that you want. So the difficulty is it's very hard to get a small gap with a cube that's resonant with the molecule. So that you're going to have to do something else. So that's the interesting challenge for all of you is try and figure out how you would do that. Okay. It's a good challenge.
Yeah, thank you.
Okay, so due to the time limit, let's thank Professor Jeremy Baumberg again for his wonderful talk, and thanks everyone for the attendance and the discussion. So yeah, just let you know that next week we will have Professor Jacqueline Block from C2N to deliver the talk about exotonic polaritons in semiconductor lattices. And the registration can be made here. And we will also send the reminder emails. So thanks again. And let's call it today.
Thanks, guys.